Wow, that seems to be a lull in the conversation. I'm going to take advantage of that, and let's get things underway here for Bio 1120 this morning. Did you see all the help we had up here today? We have real serious tech support. Lauren is confident that we're going to get the sound recorded for today's lecture as part of the integrity recording for this particular lecture. And that means that none of you will have to show up from this point forward, because if we get all this stuff working, you guys can just stay in bed as late as you like on Tuesday and Thursday mornings and won't be able to blame me for causing you to lose some sleep. So, again, we've had some issues with the sound so far. I understand that we've had some changes to the Integrity software that didn't get refreshed here, and now it sounds as if the microphone that they had issued to us is the first that has ever become defective in Wright State's experience with Integrity microphones. But, you know, Lauren seems to think things are going well. I see a little green bar bouncing around. Maybe we have sound today. Hey. At this point, half of you have made it to the lab associated with this class. All right? Now, those of you who are nodding, I can tell you are happy customers. You are delighted that you've gone to the lab. Don't tell any secrets to the people who have yet to go. Half of the class is still going there the rest of this week. But for those of you who haven't been there yet, remember you should bring some goggles with you. And it's great if you could read, I should put it more strongly than that, read the lab before you get there. It'll make things go more smoothly for you, and you'll get out of there a little bit more quickly. Okay? All right, so enough about that sort of thing. Let's just get to work and start talking about some Bio 1120 sorts of things. Let me just take a step back to sort of give you some context here. Remember, right, the first time we met, I asked you guys, what does it mean to be alive? After we pondered that deep, profound philosophical question, I started to explore with you some of the things that we can learn about living things by carefully looking at things that are not living. And we started at the really smallest scale that I know how to talk about, and that are subatomic particles. We worked our way up to talking about atoms, and in the last lecture I talked with you about what I called wet chemistry, the chemistry that's associated with water. Today I want to talk with you about organic chemistry. It's the chemistry associated with carbon compounds. And the best news of all that I've got for you is that on Tuesday of next week we're actually going to start talking about biochemistry. All right? Not quite biology yet, but biochemistry. And I'll spend Tuesday and Thursday of next week talking with you about macromolecules, the things that biochemists study. And then after that, it's all biology from that point forward. All right? So, again, I'm taking you on this crash course of chemistry so that you can understand from base principles how it is that these molecules work and are important to living systems. That's my plan. And just sort of as a word to the wise here, I hope some of you are starting to give some thought to preparing for the first test for this class. It wouldn't be too soon. Remember, on the pilot page for the course, there's a slew of old exams and answer keys that you can access. You should take a look at those, get a feel for what's going on. Today, for the first time, I'm going to be cautioning you a couple of times during the course of the lecture about where I see a path that's going to take you to a place that you don't want to be, right? And I'm going to try and point you down a different path. And the bifurcation, that split that I'm going to be trying to draw your attention to, is I suspect that most of you did well in high school because you were exceptionally good at memorizing, right? The people around you were memorizing dilettantes. You were the professionals. You got the job done, right? You give you something and you'll memorize it. That may well have worked very well for you in high school. But here, I want you to start thinking differently. I want to stretch your way of learning and your way of thinking. If that's how you learned before, I want to encourage you to set that aside. Because here, and what I've been doing for the last 3 lectures is I'm trying to get you just sort of like the base fundamental understanding of the principles that are governing all the rest of this. And I'll point it out to you a couple times today. You could memorize everything that's on some of the slides that I'm going to show you, or if you prefer, and I would prefer, that instead of memorizing stuff, you figure out how to fill out all the stuff on the slides yourself just by looking at the structure of some of these compounds that I'm going to be showing you. Knowing what you now know about valences and knowing what you now know about electronegativity, it is enormously empowering. And it saves you so much time for memorizing stuff. I want you guys to be at the point by the end of today's lecture that I flash a compound up to you, the structure, the chemical structure of some molecule, and I want you guys, just by looking at the structure and thinking about it just a little bit, not even that hard, I want you to be able to tell me if it's going to be water soluble or not water soluble. I want you to be able to tell me if it's going to want to interact with something that's got a negative charge or if it's going to want to interact with something with a positive charge. I want you at a molecular level to be able to predict and be confident that just given the structure, you know all that there really is to know that's important about these molecules. The alternative to that is that you're going to be exposed to a bunch of structures. I'm going to talk about them. They're in your textbook. They're in the lecture notes. The alternative is you could just memorize all of those details. Is it water friendly? Is it hydrophobic or hydrophilic? Is it something that's going to dissolve in water or something that's going to dissolve in a fat, right? You could memorize all that stuff, but I'd much rather you just be able to figure it out on the fly, right? Because that sort of thinking, that sort of understanding is something that's going to work for you, not just for the first test in this class. It'll work for you for the final exam for the class. It's going to work for you for the next class you take. It's going to work for you in chemistry classes. It's just a better way to know this stuff. So that's what I'm after. If you haven't looked at some of my old tests yet, there's one in the back of the lecture notes. There's a bunch on the pilot page. Take a look, and you'll start to see, I hope, more pointedly what I mean about that. All right? So again, word to the wise, that's stuff that's going to come up a fair bit during the course of today's lecture. And believe me, I suffered through a whole undergraduate degree in chemistry. I know that this stuff isn't why you guys are here. You want to talk about cute, fuzzy animals and beagles and sex and that sort of stuff, right? But to get to there and to have you really get the best understanding and get as much as you can out of those kinds of discussions, we got to work through there's no gain without some pain here at the beginning. So bear with me just a little longer. We'll get this chemistry stuff out of the way, and you'll all be better off for it. All right? So again, today's plan is I want to talk with you about the entirety of sophomore level chemistry in a typical undergraduate curriculum. In a word, that's organic chemistry. It's the chemistry that's associated with carbon molecules. That's the essence of what I'll be talking with you about. Before I get there, though, let me go back and just refresh your memory a little bit about the wet chemistry that's associated with water. This is essentially inorganic chemistry, freshman level chemistry, because I wrapped things up kind of quickly at the end of lecture on Tuesday, and some of the things that I talked about are things that you guys either have wrestled with in lab earlier this week or will be dealing with in lab today or tomorrow. So just to make sure I finish that off, and I'm going to use this as a launching board, is talk about inorganic chemistry to get us to be in a good spot to talk about organic chemistry. So here's the lecture outline from Tuesday's lecture. I talked with you about how water is such a remarkable molecule, how it is that biologists and pretty much any scientist has a hard time even imagining life in the absence of water, and especially in the absence of liquid water. Right? It's just such a unique molecule in terms of its ability to buffer temperature, in terms of its ability to act as a solvent. its cohesiveness, its ability to pull things along through capillary action and such. It's just surface tension. All of these sorts of things really set water apart. And any one of those things that I've just waved my hand at, I listed off, 4 or 5 different things. Temperature buffering, surface tension, capillary activities, solvent ability, right? Those are 4 things, and there's some subcategories to each of those 4 things. You take any one of those 4 things off of the table, and life as we know it just doesn't happen, right? All living things on this planet rely hugely on each of those special attributes of water, and you might be able to find some other molecule that gives water a good run for its money for one of those things. But man, in terms of a complete package, water is it. And so again, water is this hugely important molecule to living things. And at the end of the lecture, I finally got to talking with you about exactly what it is that this week's lab focuses on. And that's concentrations, but even more importantly, pH. Okay? And so, here is a slide that I threw at you. I had this one lingering on the screen for about 15 minutes, I think, on Tuesday's lecture. The deal is this. Water is a pretty stable compound, right? There's sharing of electrons between the hydrogens and the oxygens in each water molecule. Those are covalent bonds. You guys now know they're not just covalent bonds. We can be a little more specific and say that they are polar covalent bonds. Polar because hydrogen's electrons spend a little more time by the oxygen than they do by the hydrogen. And so there's a little bit of positive charge by the hydrogen and a little bit of negative charge by the oxygen. All right? That gives water its sort of that's the key to understanding what makes water so special, is that it's got that little bit of separation of charge. So water's got these stable polar covalent bonds. They don't just fall apart, right, randomly that often. But sometimes the sharing gets a little bit out of hand, and just sometimes, the number I gave you on Tuesday was one time out of every 554 million water molecules, the electron ends up just hanging out by the oxygen. It leaves the hydrogen goes off somewhere else, and you find yourself in a circumstance where you've got a hydronium ion, H3O, with a full positive charge, and a hydroxide ion, where you've got just an OH and a full negative charge. Right? So, tiny fraction of the time, 1 in 554 million water molecules, you should expect that dissociation to have occurred, that covalent bond to have just sort of spontaneously fell apart. Those fully charged molecules, the hydronium and the hydroxide ion, I used the phrase, they're like loose cannons on the deck, right? These are very chemically reactive. That full charge, that's the full positive or the full negative, nature gets kind of freaked out by that. Nature doesn't like separation of charge. When you've got something that's got a full positive charge, nature's looking for a way to balance out that positive charge, to hook it up to something negative and balance those full charges off. And vice versa, the negatively charged hydroxide, nature's looking for something to pair that negative charge up with. In a couple words, these are very chemically reactive. Okay? Now, living things need some chemical reactions to take place. And we can use these very reactive molecules to our advantage, right, to help move things along. There's some chemical reactions that we need to have taking place. Having these reactive molecules around is a tool that we can use to our advantage. But by the same token, loose cannons, cannons firing randomly on the deck of your ship, there might be a way that you can use those random cannon blasts to your advantage. But by the same token, you want to do something that kind of tempers them down, minimizes when it is that they'll be going off. If you got a loose cannon on the deck of your ship, Wouldn't it be nice if you could just restrict where it is that it's firing so it's not shooting right at the cabins, but rather maybe it's shooting off the bow? Because then you can point your ship in such a way that the bow is pointing toward another ship and something useful will happen when that cannon fires off, right? That's the game that we play as living things, right? We can't force reactions to occur, but we can get reactions to occur sometimes just a little bit differently than they might have otherwise, and again, that works to our advantage. So, we've got these reactive molecules, and living things use them, and they're worried about them simultaneously, and therefore, as biologists, as scientists, we need to be worried about them a little bit too, and there's this whole lexicon, this whole set of language that we use to talk about how much hydrogen ion and how much hydroxide ion excuse me, is floating around in the watery environments inside of our cells. I'll clear it out this time. All right, sorry about that. So, we worry about how much hydroxide ion and how much hydrogen ion there is, and as scientists, we worry about it to the point where we come up with words that give us a shorthand to talk about it. And so the way I described it to you on Tuesday is this. If 1 in 554 million water molecules have dissociated into essentially H plus and OH minus, that translates to a concentration, a molar concentration, that we can talk about. The hydrogen ion concentration in that sort of a watery environment is 1 times 10 to the negative 7th mole, right? 10 to the negative 7th. 10 to the negative 6th would be 1 millionth molar. 10 to the negative 7th is 1/10 millionth molar. Tiny concentration, and yet nonetheless something that has a really strong implication for the way that living things are going to be working within this environment, because those hydrogen ions and the hydroxide ions are so reactive. P, lowercase p, italics if you can pull it off. That's the way it's usually portrayed by mathematicians. Mathematicians have this jargon, this shorthand, where they say lowercase p in italics means the negative log base 10 of whatever it is that follows. Okay? And so, 10 to the negative 7th, the negative log base 10 of 10 to the negative 7th is 7. Now, if you put that lowercase p, italics, in front of a capital H, we've got ourselves a shorthand way of talking about the hydrogen ion concentration in a solution. Neutral pH, just straight up plain distilled water, straight out of the tap, hopefully, has a hydrogen ion concentration of 1 times 10 to the negative 7th molar. And in mathematical and chemical terms, that means it has a pH of 7. Now, I also told you, pH 7 is what we refer to as neutral. Okay? And I also told you that pH plus pOH always equals 14. Okay? So if the pH is 7, the pOH is also 7. Cool? That's neutral pH. But there are ways to juice up a system, to pump it up with free hydrogen ions. How, you may ask? Well, how about if you throw in a little bit of an acid? How about hydrochloric acid, just as a starting point for a discussion? Hydrochloric acid's chemical structure is very simple. Hydrogen plus chlorine. It's essentially a salt. Right? The hydrogen dissociates, the chlorine goes off in its own way. The chlorine gets a full negative charge. The hydrogen has a full positive charge. Every time you put a hydrogen chloride or a hydrochloric acid molecule into a bottle of water, you've added one more hydrogen to jack up the hydrogen ion concentration. Okay? So you can inflate, you can jack up the hydrogen ion concentration by adding an acid. That's why we call it hydrochloric acid, by the way. It increases the hydrogen ion concentration. And so it's very easy, by adding some hydrochloric acid, to get the pH of a solution to go from 7 to something like, for instance, 6. Okay? And I know this is it's counterintuitive. At a first pass, this doesn't make sense. But pH 6 has 10 times a higher concentration of hydrogen ions than something that's pH 7. But wait, 6 is a smaller number than 7. But remember, this is the negative log, right? That's why it makes sense. It's 1 millionth molar is 10 times more concentrated than 1/10 millionth molar. Isn't it? 10 to the negative 7th is 10 millionth. 10 to the negative 6th is millionth. If I've jacked up if I increase the hydrogen ion concentration tenfold from a neutral solution, I have pH 6. It's a lower pH. This is an acidic solution now, where the hydrogen ion concentration is greater than the hydroxide ion concentration. That's the definition of acidic. And if the pH is 6, the pOH, because pH plus pOH must equal 14, the pOH is 8. Okay? Now I can jack up the hydrogen concentration much more. I can get this hydrogen ion concentration to be, let's go for pH 2, right? I can put in enough hydrochloric acid to get my hydrogen ion concentration up to 1 times 10 to the negative 2, 100th molar. Everybody should, you don't need to be a mathematician to pretty quickly nod your head and say, gee, 100th is more concentrated than 100 millionth or 1/10 millionth, right? So I've really jacked up the hydrogen ion concentration for pH 2, 1 times 10 to the negative 2 molar, in other words. If the pH is 2, not only is it really acidic, but the pOH must also be kind of out of whack, right? And it's going to be 12, because pH plus pOH always equals 14. Okay? So simultaneously, when I'm increasing the hydrogen ion concentration, I'm also at the same time going to be decreasing the hydroxide concentration. Okay? Low pH, a low number for pH means we're talking about something that's acidic. A high number, bigger than 7, means we're talking about a solution that we can call basic. And so just as I can jack up the hydrogen ion concentration, there are other molecules that I might put into water that would jack up the hydroxide ion concentration. The simplest of which would be something like sodium hydroxide. Right? Sodium hydroxide is another salt. Here, the sodium dissociates and comes away as Na+, a positively charged ion, and the hydroxide goes away, carrying a negative charge with it, OH-. So for every sodium hydroxide molecule that I add to water, I am going to increase the number of hydroxide ions in that solution by 1. Now, if I do this enough times, it's not too hard for me to nudge up the pOH from, say, 7 to something like 6. Right? So pOH is, again, the sort of the flip side of the coin. And I can increase the hydroxide ion concentration. At the same time that I'm doing that, I'm also going to be driving down the hydrogen ion concentration. So if I've made a solution pOH 6, I will have simultaneously made the hydrogen ion concentration 8. If pOH is 6, then pH must be 8, because pH plus pOH equals 14. Long and the short of it is simply this. Basic solutions have a large number, larger than 7, for the pH, and a small number for pH. Means we're talking about something that's acidic. Okay, so acidic things have small numbers for the pH. Basic things have large numbers for the pH. And the converse is true for pOH. Almost always in a biology class, you're going to keep your eye, it makes it easier if we keep our eye on the ball of the pH. But you should also know in the back of your head, there's this POH thing that's going on as well. And if you want to be really, you know, a smart aleck about things, when you're talking to a chemistry professor, you can translate pH to POH and just say, oh, well, professor, the POH here is this. And they're like, why are you talking about POH? You know, it's the pH that's the thing that everybody else in the room is talking about, but they'll appreciate that there's an equivalency between the two. All right. Now, in lab this week, what you've done and what you're doing is you're checking out, you're measuring hydrogen ion concentrations and hydroxide ion concentrations at the same time. And so this figure out of your textbook answers some of the questions that you're supposed to be answering before you get to lab this week. What's the pH of blood? pH of blood is in the ballpark of 7. There's a specific answer, right? I think it's 7.3 or 7.4. It's in that range, right? So it's slightly basic. If the pH of your blood gets to be 8, we've already talked about this. There's a med school class in here as well. pH of 8, we call that dead, right? pH of 6, we got a term for that fancy term, 4 letters dead, right? If you mess around with the pH of your body very much, you're in a world of hurt. Unrecoverable error, right? You got issues. So humans operate in a very narrow pH range, but it's not just us. Everything that's alive operates in a very narrow pH range. Now, some things operate in a different pH range than we do, right? But we all work in a very narrow range. And things that you encounter all the time can have really very different pHs. Ammonia is a very basic solution. Look at that, household bleach, pH of 13, right? That's crazy. You don't want to be touching bleach because that's really radically different than the pH that your body is designed to be working best at. The more that your body or your finger or whatever's pH starts to look like bleach, the worse your troubles are going to be. Because your proteins, your body isn't set up to work in those sorts of crazy extreme hydrogen and hydroxide ion concentrations. Right? Oven cleaner. Need I say more? Right? Not a good thing to be messing around with because it's such a different pH than the rest of your body. How many of you guys think that sucking on a battery and getting the acid out is a good idea? I'm telling you, this isn't wise, right? It's not wise because battery acid is insanely acidic. That's why we call it battery acid, right? It's got a really wildly different pH and POH than what it is that we're geared up to working with. But other things like, lemon juice and your stomach's digestive juices use these different concentrations of hydrogen and hydroxide ions to their advantage to help foster, to encourage certain chemical reactions to occur in a contained space where it can't do much damage to the rest of you. Right? So again, look at all of these different things that we encounter that have different pHs, that are well suited for what it is that's going on for that particular thing, but again, not necessarily well suited for other things that we might want to have going on. All right, so that's what's going on in lab this week. Let's now spring into talking a little bit more about organic chemistry. I want to focus now. We've beaten water to death. Water is special because it's got these polar covalent bonds, right? Look at that structure. Look at that structure, right? Actually, look at all 4 of those structures. The one on the top of the screen, I'm not looking, but I'm thinking it's hydrogen gas. Am I right? I've seen this slide before. Right? You have too. The one on the top is hydrogen gas. What can you tell me about hydrogen gas? How will it behave, as a chemical? How will hydrogen gas what will it like to do? Will it be a liquid? Will it be a solid? Will it be a gas? The name says gas, so that's kind of an easy question. But why is it a gas? Why do we think of hydrogen gas as a gas as opposed to a liquid or as opposed to a solid? Yes?
Is it because due to the fact that they're equally sharing, there's not going to be many intermolecular attractions
You got it.
between the
Let me
molecules.
say it loud so everybody in the room can hear. Hydrogen gas is a gas because hydrogen atoms have exactly the same electronegativity. When you share electrons between two hydrogens, you truly share the electrons between two hydrogens. This is the very epitome. You can't get a more nonpolar covalent bond. Right? It is the definition of a nonpolar covalent bond. There's equal sharing of the electrons, and that in turn means there is absolutely no separation of charge from one end of the hydrogen gas molecule to the other end of the hydrogen gas molecule. Okay? In the absence of that separation of charge, what's the basis for this molecule to interact with other molecules? That separation of charge almost always is what governs how it is a molecule is going to behave. It has no separation of charge. It is about as inert of a compound as you can possibly make. Right? It doesn't even like to interact with other hydrogen gas molecules. That's why it's a gas. Very plainly, that's why it's a gas. One hydrogen gas molecule bumps into another hydrogen gas molecule and says, hey, get out of my way, I don't want to see you anymore. And they're physically separate from each other at a molecular level. Gas, they're floating around. Apply that same sort of thinking to the next molecule down, oxygen gas. Right? Oxygen gas is a sharing of electrons between two atoms with precisely the same electronegativity. Now, I've been beaten up on oxygen. I've been telling you oxygen's about as electronegative an atom as you're going to be encountering in this class. But fine, oxygen's an electron bully, but you got two electron bullies going toe-to-toe here. They're equally electron bullies. They're equally greedy for electrons. They share the electrons equally between them. This is another definition of nonpolar covalent bond. There is no basis for one oxygen gas molecule to interact with any other oxygen gas molecule or any other molecule for that matter. All right? It's pretty chemically inert. There's not a lot of intermolecular interactions going on here. That's a gas. That's why we call oxygen gas. That's why there's oxygen in our atmosphere as opposed to under our feet. Right? Check out water. The next one down. You guys know the rules, right? You're playing a game here. Nature set up a board game. Nature's got, 4 rules that are part of this game. One of those things is that, boy, you really like to have your outermost shell of electrons either completely full or completely empty. Right? Another rule is that, separation of charges, not a good thing. Avoid that if you can. Are there other rules? I think that's it. We'll get into some implications of those rules down the line, but nature hasn't come up with a particularly complicated board game here, right? It's based ultimately on 2 rules, and then there's strategy that gets layered on top of those rules as you play the game, but that's pretty much what's driving the whole conversation. Look at water. I've been beating water to death now, too. Good grief, 2 lectures I've been talking about nothing but water. Check it out. You guys don't need me to repeat this. In fact, you guys, if you understood these rules at the beginning of lecture on Tuesday, nothing that I've said is inconsistent in any way with those rules. You could have played out the whole thing in your head. I could have been very Socratic. I could have been like Socrates and said, well, here are the rules. You tell me how it all plays out. That structure for water, we're talking about covalent bonds, no longer non-polar covalent bonds, but polar covalent bonds, because hydrogen and oxygen have different electronegativities. Right? So there's an unequal sharing of electrons. That means there's a partial separation of charge. That means that water molecules, At room temperature, in our kind of environment, we kind of expect there to be a fair bit of intermolecular interactions going on. That means it's a liquid. Pretty much plain and simple. When you have a fair number of interactions taking place, well, that's sort of what happens in a liquid kind of circumstance. If you juice up the system, give those molecules a lot of energy, yeah, I suppose you can pull them apart. Okay, that's gas, that's steam, right? And if you take the energy away, you can convert that liquid into a solid, and that's ice. Right? And you can play those sorts of games. But now, here's a sort of a payoff kind of question for you. Right? This has all been a prelude to this one big question. I don't think we've talked about that fourth molecule in any substantive way so far in this class. I think I've mentioned the name. The one at the bottom of the screen is methane. You guys might have some ideas about what methane is and how methane gets used and how you might purchase methane, right? And that might tip the scale in terms of your understanding what it is. But forget everything you know about methane, if you can, and just look at that structure and think what's going to happen. What's the characteristic? Is this going to be a gas or a liquid or a solid? Is it going to want to dissolve sodium chloride? Is it going to want to interact with water? What's the story for a compound with a structure like that? Carbon with 4 hydrogens. Right out of the gate, here's some things that you might want to do just to make sure, you know, sort of like a check on this, that you're not getting tricked or fooled. Is that a plausible structure? Carbon with 4 hydrogens in a covalent bond. The fact that it's up there, yeah, okay, you got a leg up on that one too. But if I had carbon with just 3 hydrogens, you'd be saying, oh, wait a minute, somebody's trying to pull a fast one because carbon wants to make 4 covalent bonds, right? It's got a valence of 4. And so that's cool. Hydrogen has a valence of 1. Each hydrogen wants to make 1 covalent bond. Okay, this is all cool. It's all checking out. Just keeping you honest. Let's move on. What can you tell me? What do you think about the electronegativity, the relative electronegativity of hydrogen and carbon? Hydrogen, half empty, half full. Give an electron, take an electron, it's all the same to hydrogen. Carbon, half empty, half full. Right? It needs 4 to round out its outermost shell. It needs to ditch 4 to empty out its outermost shell. What's the difference between half empty, half full, and half empty, half full? I said the same thing, right? This is sort of like a truism, right? That A is A. A is not necessarily B, but A certainly is A. Half empty, half full, half empty, half full, hydrogen, carbon, they've got the same relative electronegativity. You want an electron, take it. You don't want an electron, I'll take yours. I don't mind. That being the case, what kind of covalent bonds? There are 4 covalent bonds in that structure. They're all the same, all hydrogen to carbon. Do I have any choice but to call those covalent bonds non-polar covalent bonds? Anybody want to fight me here and suggest that they should be polar covalent bonds? I want to hear the argument that supports the idea that these are polar covalent bonds. I'm a little afraid to hear the argument, but I want to hear the argument because you're wrong. They have the same electronegativity. There's going to be equal sharing of the electrons between them. Those are pretty close to the epitome, the definition of nonpolar covalent bonds. We got A, B, C, and D there. 3 of those compounds have nothing but nonpolar covalent bonds. 1 of them has polar covalent bonds. Therein lies all the difference in the way that for why it is these molecules act differently. 3 of those molecules at room temperature are gases. 1 of those is a liquid. That's why. Methane you buy at Meijer, and by the way, if any of you work for Meijer or Kroger, or Domino's Pizza or whatever, I'm really good at product placement. I can slip in a promo for just about anything in the course of one of these lectures. All I need is a little bit of payola, right? You know, Domino's Pizza, wouldn't it be, how about Krispy Kreme? Any of you work at Krispy Kreme? Because I can slip Krispy Kreme donuts into every lecture, like 10 times a lecture. All I want is like a couple dozen free donuts, and we'll share them with the whole class, right? I'm very open to this, so, you know, just as an aside. But when you buy methane gas at Meijer or whatever supermarket you work for, you buy methane gas, right? And why is methane a gas? Methane's a gas because it's got nothing going on there but nonpolar covalent bonds. One methane molecule has very little basis to interact with any other methane molecule. One methane molecule has very little basis to interact with any water molecule or oxygen or hydrogen gas molecule. What do you think? Is methane gas going to be very soluble in water or not very soluble in water? If there's no basis for interaction, there's no basis for taking it up in solution. Methane, excuse the language, is a crappy solute. It doesn't dissolve very well in water. What can you say about oxygen gas? Believe it or not, oxygen gas is also a crappy solute. Water, I don't know. I guess we can fit some oxygen molecules in here somewhere. But water's not going out of its way to suck up and absorb and dissolve oxygen gas. There is no basis for a chemical interaction. How about that? You don't need me anymore for this stuff. And from this point forward, I'm going to be seriously inclined, and I'll challenge you. I'll say, look at this structure. Look at it, right? And you tell me how it is that it's going to behave. And I'll point you out a couple other little nuances, some other strategic sort of things that come from these two basic rules that nature has in its board game. But the bulk of it, you know now. If you know how to apply those rules and you can decide, is this going to be a liquid or is it going to be a gas? Is it going to be something that water likes to dissolve or water has nothing to do with? Man, that is 80, 90% of what's important about chemistry for biology. And frankly, anything about chemistry that's not important for biology is a kind of a waste of time. But that's just my personal opinion. All right. So, pop quiz, right? Are you surprised to hear that sodium chloride dissolves well in water? I hope not. I've said this before. But I think you have personal hands-on experience with this going back to when you were in preschool, right? If you put salt into water, it dissolves pretty well. Salt is a solute, and water is a solvent. That's a match made in heaven. With a little bit of positive charge on the hydrogens in water molecules loves to nestle up against that really big, sweet-looking negative charge on the chlorine ions. And that little bit of negative charge on the oxygens just loves to get a piece of some action associated with the positively charged sodium ions. Everybody's happy. The sodium's got like 10 friends. The water's hanging out with the cool kid on the block, right? Everybody is happy. Salt dissolves very well in water. What do you get? You get salty water when you mix salt with water because of that structure of water. But again, today I'm talking with you about organic chemistry. Enough about this inorganic stuff. Enough about water for a little while. Let's start thinking about how compounds that have carbon within them will behave chemically. And so this particular slide shows you 4 different ways that carbon molecules might differ from other carbon molecules. We tend to, when I throw a structure of a carbon molecule at you, you might want to evaluate it just as a first pass, on the basis of these 4 different sorts of ways of thinking about carbon. The first is just how long of a molecule it is. Methane is as short of a carbon molecule as you can get. It's carbon with 4 hydrogens. But I'll tell you, all of the structures you see up there are equally valid chemical structures. You can test it if you like, but every carbon has 4 covalent bonds associated with it. Every hydrogen has 1 covalent bond associated with it. Right? So they're all good structures, but methane is when you've got a chemical structure, the formula is CH4. There's just 1 carbon. Ethane has a different chemical structure because it's a little bit of a longer chain of carbons. Here you got 2 carbons and you got, 6 hydrogens. So the structural formula is C2H6. Okay? Pretty simple stuff. And propane is just a little bit longer of a chain still. There's no practical limit to how long you could make that carbon chain. And after a point, organic chemists have gotten tired of giving specific names to those compounds, but you'd be surprised they go up to about 20 or so before you start to have to just give the structural formula. So, but nonetheless, one thing we might look at is the length of the molecule. Okay? Simple concept. Look at B. It turns out that you can dress these carbon compounds up in different ways. Once you get to a certain length, you can get molecules that have the same structural formula, the same chemical formula. That's probably a better way to put it. You can get molecules that have the same chemical formula, the same number of carbons and hydrogens in the formula, in the compound, but different structures. For instance, butane has 4 carbons and 10 hydrogens, and methylpropane, also commercially available as isobutane. Methylbutane has 4 carbons and 10 hydrogens. You don't need to be a particularly sophisticated chemist to be able to look at those 2 structures and say, oh, they look a little different, don't they? All right? The same number of carbons, the same number of hydrogens, they're just arranged in different ways. Chemists call that an isomer. Same chemical formula, different arrangement of atoms. And so this is a structural isomer because the structure of the molecule is obviously different between the 2 of them. What do you think? How will butane behave? Right. Off the top of your head, what do you think? Well, I see nothing here but nonpolar covalent bonds. That sounds to me like it's got all the makings of a gas. All right? There's no basis of interacting. I can tell you this really comfortably. It's sure not going to have much to do with water, and water won't have much to do with this. Is butane water soluble or not? Not is the right answer to that question. Is it a gas or not? Yeah, well, you guys all know about butane lighters. I guess when you click them, the butane comes out as a gas and it catches fire. Okay, yeah, it's probably a gas. But I worry a little bit about butane in terms of its gassiness because that chain's getting kind of long. Those longer molecules, it's harder to give them enough energy to get their acid or the molecules out of the chair and floating around the room. Right? I don't know, can we bleep things on this? I don't know. It's hard to get these molecules to move around just because they're so big and bulky. They need to go on a diet, right? Is what it comes down to. So I don't know. By the time you're up to 7 or 8 carbons, I'm thinking, okay, it's certainly not water soluble, but it may just be too big, absent a lot of heat and energy to get it moving around to become a gas. Maybe it's going to be a liquid. So I worry a little bit about its gaseousness versus liquidiness, right? But butane certainly won't be water soluble. No basis for interaction with water. Probably a gas. I'd put my money, if I had to bet, on butane being a gas. I'm feeling pretty good that I'd win that bet. But you guys know why I'm talking about butane here, right? Because I want to do a compare and contrast between butane and isobutane. All right, so I've told you what I think about butane. What do you guys think about isobutane? Anybody want to say, was that ditto? Because that's what I was looking for. Butane and isobutane, look at those structures. Do you think isobutane's going to behave that much differently than butane? I don't see any reason why it should. you know, there may be some subtle differences. A long chain might get tangled up in some way with other long chains more than a little T structure would. I could kind of argue myself in the other direction, too. So, I don't know. I don't think there's going to be much difference chemically, behaviorally, between butane and isobutane. And believe me, I'm not an authority on this. Just looking at the structures, that's my best guess. And that's all I'm going to be asking you guys to be able to do as well. So here we've got two structural isomers. They're different. I suppose we can start to imagine how the difference in the structure could give rise to some differences in the way that these molecules behave. But the difference here isn't that big such that we're going to be screaming water soluble as opposed to insoluble. Yeah, no, that's not going to happen here. All right? And that's the way I hope you guys start to think when you're confronted with these kind of molecules. Let's move on. C. Okay? Now we haven't talked about, I guess I did talk about this a little bit. Oxygen gas makes two covalent bonds, right, between one oxygen atom and another oxygen atom. Carbon can make two covalent bonds with another carbon atom, or an oxygen atom for that matter. And that's with that equal sign. So you see one butene up there. I'll point to it. That's probably better. You see that? Looks sort of like a stretched out equal sign. That's chemical shorthand. It's a chemical notation for a double bond. That means we've got two nonpolar covalent bonds going on over there. What do you think? That chemical structure look like it's fair? We've already covered this, right? Every carbon's got 4 covalent bonds. Every hydrogen has 1 covalent bond. It passes that quick test. It's a plausible structure in that sense. You can see that you can put that covalent, that double bond at the beginning of butene, or you could bury it in the middle. Let me tell you, chemically speaking, the way those molecules are going to behave, not that different, right? Neither, guaranteed, I'll bet a lot, they are not water soluble, right? Gas versus liquid, probably gas, it's a pretty short chain, right? They're going to act an awful lot alike. But, again, there's a little difference there. What do we call molecules that have the same chemical formula, the different structures? Well, they're isomers at the very least. This is another kind of structural isomer, just like butane and isobutane are. Let me ask you this. What if the double bond, you get the nomenclature here, right? The double bond starts on the first carbon, carbon 1, 2, 3, 4. The double bond is there, so that's why they call it 1-butene. This one, the double bond starts on the second carbon. They call that 2-butene. What if you put the double bond over here? Do you suppose there's such a thing as 3-butene? You might think that there is, but there isn't, because 3-butene and 1-butene are the same things, just get flipped around. Okay? So, anyway, just a little bit of an aside there. If you're freaking out about the names, you'll never have to, believe me, I'm not going to give you an exam question where I ask you, is this 1-butene or 2-butene or isobutane or, butane? I'm not into those sorts of goofy names that chemists have attached to these things, but there is often a method to the nomenclature they use. All right, one last way you can press up a carbon compound. Need I say more? You can bend the chain around and you can make something that gets the fancy name. I think chemists spend a lot of time thinking about this. You can get something that they call a ring. All right? So when the carbon chain gets bent around and comes back on itself, you can have a ring. You can have a ring that gives rise to a structure like cyclohexane, or a ring that gives rise to a structure like benzene. You'll notice the difference between cyclohexane and benzene is that benzene has some double bonds within the ring, where cyclohexane does not. You'll also notice that when you draw this sort of structure, this is a chemical shorthand that means this. So when a chemist draws something like this, at each of the angles, like here and here and here, that's supposed to conjure up in your mind the idea of a carbon atom. I'm not joking. That's what they've come up with. All right? So whenever you see an angle like that, that means there's a carbon there. And chemists are going to presume that you're clever enough to know that if you've got a carbon that's involved in a covalent bond to two other carbons, that it's also going to have to round things out with something else because it needs to make 4 covalent bonds. If they don't say anything about it, they presume that you will presume that those other things are hydrogens. So that structure to a chemist translates directly and unambiguously into this more detailed structure. So if somebody throws a ring structure like this out at you, they're expecting you to know at each of the corners, at each of those angles, there's a carbon, and wherever you need to invoke hydrogen to round out the number of covalent bonds for carbon, you round them out with hydrogens. And if it shouldn't be a hydrogen, they'll tell you what it is that it should be there. So a little bit of shorthand. You'll see this time and again, I'm afraid, during the course of the rest of this class. Now over here, what they've done is they've shown you where the double bonds are. Wherever there's this angle, there's a carbon, and if you need something to round out the valence of carbon, here you've got what, 1, 2, 3, there must be 1 hydrogen. Oh yeah, look at that over there. They show you the hydrogen explicitly, but they usually won't go through the trouble of showing it to you. They'll just show you the ring structure with the double bonds and let you fill in all the rest if you really care to. Okay? Big question about these things. Cyclohexane and benzene. Big question. At a first pass, just at a glance now. Now I want you guys to be convinced that when somebody flashes a chemical structure at you, you think water soluble or not? Big not. All right? No basis there for water to interact. Liquid, solid, gas, I don't know, maybe gassy. Maybe liquidy, probably not a solid, not big enough to be a solid. We'll get into those sorts of things in a little more detail in lecture on Tuesday. But there you go. That's what I hope you see. At the very least, you should look at that structure and you say, oh man, that's not going to be dissolved. You can't dissolve that in water. It's going to be really hard to dissolve that in water. And at the end of the day, here's another truism that I think you learned in preschool, right? Oil and water just don't mix. You guys now know at a molecular level precisely why oil and water don't mix. Right? You guys know. It's not so much that the oil wants to interact with other oil molecules or fatty things, right? It's just that water doesn't want to play with them. And so it's excluding them. So one water molecule says, I'd much rather cozy up against another water molecule than you fat or oil molecule. And so what ends up happening, it's a shunning. It's a molecular shunning. Water's behaving very badly, right? No, we don't want you. You go over there. And all of the oil ends up getting pushed off to the side, and the oil molecules end up just hanging out together because they can't interact with the water, and they're not opposed to the idea of interacting with themselves because they've been shunned. Okay? So oil and water don't mix, and that's why. All right, check it out. I am 3 lines down on this lecture outline. Don't worry, the rest goes really fast because of the other things that I've been talking with you about so far. So I feel right now I've said all that I care to say about valences and about isomers and carbons bonds, and it's time to start talking about carbons functional groups. I got great news for you guys, really good news. If you played around, just used your imagination, you could probably come up with tens of thousands of different compounds, chemicals that you could dangle off of a carbon molecule. Right? It wouldn't be hard at all. But the good news is this. Nature really ends up using just 7. These are the 7 that you see time and again playing an important role in the structures of molecules that living things rely upon. Nature, biology, dresses up carbon molecules with just 7 different functional groups. The good news from the second lecture of the class was there are 92 naturally occurring elements. We focus our attention on 4 because they give us a palette that you can make a wide range of different kinds of molecules with. Now we're going to use that palette to paint some things out that have their own special chemical characteristics. And we tend to go to the well time and time again and use just 7 of these structures over and over again. Okay? I'm optimistic, I'm confident actually, that I don't need to say much about these 7 structures, because when I flash them on the screen to you in the course of the next 15 minutes, first thing that I hope you'll do is when you see that structure, you're going to think to yourself, gee, is something with this dangling off of it going to be water soluble or not? Right? That's the first thing I hope you think about. And then, I'm sorry, but there's some vocabulary we need to go through as well. And there's no easy way to do this. I'm afraid you have to memorize it. But compounds that have these things dangling off of them get special names, right? And so we need to talk about what those names are. And I'm afraid you need to memorize them because we'll be using that vocabulary as we talk about other molecules down the line, right? But that's it. So let's get to work and talk about how it is that you might be able to dress up a carbon molecule. Here's exactly what I'm talking about. You got ethane here. There's a structure. That's a carbon molecule, the way that I'm talking about them now. What if you got rid of that hydrogen and tacked something else onto it in that spot? All right? There are 7 different things that you'll find biology likes to use in that way, to take the place of one of those hydrogens in a carbon molecule. And each of those 7 imparts its own sort of special chemical flavor and chemical tendency to the molecule. All right? So the plan now is just to go one by one through each of those 7. We'll go one by one through each of these 7 different kind of functional groups, talk about what it is that that does to the molecule, and what it is we call those kinds of molecules. Need I say more? Right? Hydrogen likes to make 1 covalent bond, carbon likes to make 4, oxygen 2, nitrogen 3. They have different electronegativities aside from hydrogen and carbon, which have the same electronegativity. You got that under your belt, and you can predict all the rest of what it is that I'm going to tell you about the chemistry here, just with that in mind. Oh, hey, and this is fun. Remember, I think it was in the first lecture, I said it's hard for us to imagine life without carbon, and yet the Star Trek guys got challenged at one point, the writers, to come up with something that didn't look like a human with pointy ears as an alien. There's got to be something else out there, guys. Here, I've got a picture for you here of what life based on silicon might look like. Right? So here's carbon, right? If you wanted to get rid of carbon as one of your 4 key elements for living things, maybe you could substitute silicon. There it is. There's the Horta. Comes straight from StarTrek.com, a very authoritative source. That's a joke, by the way. I'll tell you, 2 years ago when I showed this slide, I had a student come up to me after class, clearly from some other country, not familiar with Star Trek apparently, and they were very intrigued. They were excited about Hortas and where they might find a Horta, and looks like it might be a nice pet, and do they hurt goldfish? And, I was, oh my gosh, no, wait, we got to take a big step back. Okay, despite, it turns out Star Trek is science fiction. It's not really true, right? But the writers of Star Trek got challenged to come up with some alternative to life that isn't carbon-based, and the Horta, this rock-based, silica-based thing from Janus 4, right, is their best solution to it. All right. an interesting episode of Star Trek. We've talked about these structures before, right? How they can, this slide for me is just here to help me convey to you how there are equivalent ways that you can think about these molecules. Methane, we could just talk about its molecular formula, CH4. You could talk about its structural formula where you lay it out that way. If I show you a compound on an exam, this is about as sophisticated of a drawing as I'm going to give you. But if it helps you to think about the ball and stick kind of way of representing it, that's fair. And even better, when I try to think about something like methane, I try to conjure up that space-filling model to imagine how it is that this thing might bump into and interact with other molecules. And you can see how these other structures might have different shapes. All right, and those are the compounds that we're going to dress up. Let's just get all past that. So there are other ways that you can make isomers. I thought I was done with those first 3 lines of this outline, but there are other ways you can make isomers. You can make cis and trans isomers. Check it out here. Cis means that the thing that's dangling off, the things that are dangling off are on the same side of the molecule as opposed to different sides. I'm not going to ask you about that on a test. All right. The handedness of the molecule can look different, right? So they can have the same number of atoms, but they can be arranged in a way such that I got the same number of fingers and the same number of thumbs on each hand, and they look at a first pass similar, but I can't quite put one on top of the other in a way that has them line up. I got a left hand and a right hand. So there's another kind of structural isomer that's called an enantiomer. Living things, pay attention to the differences in those isomers, the handedness of the molecules. If you have S-ibuprofen, and if you're really curious, if you're looking to win at a biology trivial pursuit game, S is short for sinister, the Latin word for left. Did you know that? And R is short for right. So you have the left-handed and the right-handed version of these. One of these has no biological activity. The other has a lot of biological activity. That's why we use ibuprofen. The ibuprofen you buy from the store has probably been purified, so it's just the active version as opposed to a mix of the active and the inactive version. And the same is true for albuterol. All right, but enough of that. Here they are, the 7 functional groups. Can you read those? It's in really tiny print. Right? Part of that's by design, but part of this is just an overview. So there, you got 3 of the 7 right there. This table comes straight out of your book. You got the other 4 of the 7. This table comes straight out of your book. The next 7 slides just focus on each of those individual molecules. Right? So the book shows them to you, 3 on one page, 4 on another. Now let's just focus our attention one at a time at what it says about each of the 7. Okay? Top of the list, first one of these 7 functional groups for us to talk about is a hydroxyl group. Let me remind you, what we're talking about here when we're talking about functional groups of carbon is all I mean is this is something that you could tack on in the place of one of those hydrogens that's attached to the carbons in a carbon compound. With me? So ethane had 2 carbons and 6 hydrogens. All I'm saying is I could take one of those hydrogens off and replace it with something else. I want to talk about replacing it right now with a hydroxyl group. A hydroxyl group is an oxygen with a hydrogen. Look at this chemical structure. Oxygen, always shown as red, another chemical shorthand. Hydrogen, always shown as a small gray ball, more chemical shorthand. This oxygen, at some level, I hope you think that doesn't look right, because this oxygen is supposed to have 2 things that it's attached to. Well, I'm telling you, I want to attach it to carbon. All right, so it's dangling off here. Somewhere around over here, there's a carbon, always shown as a black ball. There's going to be a carbon that I could dangle this hydroxyl group off of. So picture ethane, strip away one of those hydrogens and put in its place an O and an H. The O is happy. It's got a covalent bond to the carbon and a covalent bond to the hydrogen. The hydrogen is happy. It's got a covalent bond. All this valence stuff has been satisfied. But now, ethane, which before, when we considered it, was unambiguously a gas, unambiguously not very water soluble. What's going to happen if I put a hydroxyl group onto ethane? It's changed. It's going to have a different chemical flavor. It's going to behave differently. It's got now, oh hey, I was making this stuff up all out of my head. I had no idea that the slide actually showed you ethanol, right? Because that's exactly what happened here, is they took ethane, they stripped away a hydrogen, and in its place they put a hydroxyl group. That molecule is going to behave differently than ethane did. Water soluble or not water soluble? What do you think? It's got some basis for interacting with water now, doesn't it? Now, part of the molecule is still pretty antisocial, right? The carbon with the hydrogens part, right? But part of it, now water can sink its teeth into. And so it may not be hugely water soluble, but it's going to be much more water soluble than ethane was. So you tack a hydroxyl group on a molecule, and it's going to tend to increase its water solubility. It's going to tend to increase the ability of this molecule to interact with other molecules, including other molecules of itself. Why? Because this here is a polar covalent bond. You should expect this oxygen will suck away some electrons from the carbon, and it's going to suck away some electron from the hydrogen. It's going to get a little bit of a negative charge. That's going to have a little bit of a positive charge, and there's going to be a real tiny whiff of positive charge associated with all the rest of the molecule. But most of the positive charge will probably be concentrated here, and the negative charge will be concentrated there. Ethanol has a good basis for interacting with other molecules, including water. Now, that's the most important part about this structural group, this functional group of carbon. The fact that if you tack on a hydroxyl group, you're going to play some games that influence the water solubility and the flavor, the kind of molecules that this molecule will now want to interact with. Then there's some trivia, okay? I can't do anything about it to make it less trivial aside from telling you this. If you put a hydroxyl group on a molecule, that molecule now gets called an alcohol. That's it. That's all there is to it. If you put a hydroxyl group on a molecule, chemists now start talking about this as an alcohol, and the name of the compound is typically going to end with OL at the end. Ethanol, methanol, isobutanol, all of these are different kinds of alcohols. And all that means is there's carbons, chains of carbon, that have a hydroxyl group tacked onto them somewhere. Okay? The alcohol that is in beer and wine and vodka is ethanol. That's the specific chemical structure for the alcohol that people will typically consume. That's one of them, all right? We can go through the rest of these even faster. Another thing that you might dangle off of a carbon chain is simply this: an oxygen that's got a double bond to one of the carbons in the carbon chain. What do you suppose is going to happen? How's that going to change the chemical flavor of a molecule where this functional group, a carbonyl group, is in place? Well, that oxygen's an electron negative bully. It's going to pull electrons off of the carbon. It's going to get a negative charge. That carbon's going to get a little positive charge that'll probably get spread across over the course of the rest of the carbon chain. More water soluble or less? It wasn't at all water soluble before. You can only go up. This tends to make it pretty water soluble because you got that glowing now negative charge, or a fairly strong negative charge at one point on the surface. Any molecule that has a carbonyl group we call a ketone or an aldehyde, depending on where it is that the double bonded oxygen gets tacked on. If it's on the end, we call it a it's on the end. You can tell I don't know, right? So you guys don't have to know either. Let's just move on, right? So, and I'm serious, right? Because I can tell you this. If you put a carbonyl on it, I know it's going to make it either an aldehyde or a ketone. If I really got to know the difference between an aldehyde and a ketone, I know how to look it up, all right? You guys will know that too. And I'm not joking. I mean, that's entirely serious. But chemists have this jargon. You put a carbonyl group on, and I hope you will remember it's either an aldehyde or a ketone. And it's going to make it a little bit more reactive because it imparts a little bit of a negative charge to one part of the molecule. Functional group number 3. We talked about what carbonyl groups and hydroxyl groups. Now number 3 is a carboxylic acid, or a carboxyl. Slipped in acid. Carboxyl almost always has acid associated with it. Look at that structure. You got a carbon with a double bond to an oxygen and a hydroxyl group. Boy, that's just screaming out polar bonds, right? In fact, they're so polar that you should expect this to be pretty easy to ionize, pretty easy to get the hydrogen to fall off and have it act like an acid that increases the hydrogen ion concentration and lowers the pH. And if you dangle something like this off of a carbon chain that has a full-blown negative charge on it, oh my gosh, water's going to love it. It's going to make it hugely water-soluble. And it's also going to make it really appealing to any molecule that has a full-blown positive charge. Might there be such a thing? Well, let's see if there's another functional group that fits that bill. If you put a carboxylic acid on it, we call it, or if you put a carboxyl group on it, we call it a carboxylic acid. How about this? Now we got something that has a positive charge. Right? If you dangle an amino group off of a carbon chain, what you're doing is you put a little bit of positive charge, not even a little bit, you put a full-blown positive charge on one part of that carbon molecule. Amino groups are nitrogen with 2 hydrogens dangling off of it, and they have a real strong tendency to pick up a hydrogen because of the valences that are in play here and get themselves a full positive charge. If you put an amino group onto a carbon compound, we call those molecules amines. 4 down, 3 to go, less than a minute each. Another thing you could dangle off of a carbon chain would be not an OH, but an SH, S for sulfur. These are sulfhydryl groups. If you put a sulfhydryl group on a carbon compound, we now start talking about that carbon compound being a thiol. Another bit of trivia for you to commit to memory. Neat thing about thiols is that living things will often use a thiol on one molecule, a sulfhydryl group on one molecule to make a covalent bond to a sulfhydryl group on another molecule. So you sort of staple the molecules together. You make what are called disulfide bonds. When we talk about protein structures a week from today, that will be a term that we use a fair bit. What if you want to have something that's not a carboxylic acid, but still has a raging negative charge associated with it? Really hardcore negative charge. I got a functional group of carbon for that. That's called a phosphate group. So we can take phosphorus, which has a valence of 5, a little bit unusual. We haven't talked about these, but it's on a different place in the periodic table. Phosphorus has a valence of 5, and it tends to have not just one negative charge when you dangle it off of a carbon chain, but 2 full-blown negative charges right next to each other. It freaks nature out. That's an itch that's got to be scratched. Sometimes you got an itch that I can wait until class is over to take care of. This is one you deal with right away. It's a flaming negative charge. So you want a carbon compound to have a full-blown double negative charge phosphate groups are what you need. And you just want to neutral things out. Well, you could dangle a methyl group off of it. That's just a carbon with 3 hydrogens, and that's sort of like as milk toasty as you can make a molecule. Not water friendly, just sort of hangs out like part of the carbon compound. And those are the 7 functional groups that we use to create the molecules that living things play with. There's lots of other ways you can dress up carbon molecules. Nature doesn't. It uses these 7 pretty much to the exclusion of everything else. Tuesday, we'll talk about how you can make big molecules from small ones. Have a good weekend.